Yeah, thank you very much for the invitation. It's an honor to speak in the seminar. So I'm going to tell you guys about a project of mine on band sums. And the project is motivated by a conjecture called the Cosmetic crossing conjecture. It's a conjecture in knot theory. So let me tell you about that first. So I'll give you an imprecise version of the conjecture on this first slide and give you a slightly more precise version on the next. So here's what's called a nugatory crossing change. What you've got are two knots and you form their connected sum. And in the band along which you form that connected sum, you add a little twist, so you see a crossing. And this crossing is called a nugatory crossing. And you'll notice that if you change a nugatory crossing, the knot itself doesn't change. So this knot up here is the same as the knot down here. The cosmetic crossing conjecture is the conjecture that this is the only possible way to do a crossing change and to not change the knot. Perhaps more precisely, the only way to change a crossing and not change the oriented knot type. Okay, so here's my setup. I've got two oriented knots, K plus and K minus, inside the three sphere, and they differ by a crossing change. So outside of a ball, they're the same. And inside the ball, K plus is a positive crossing, K minus is a negative crossing. And I'm going to then take the oriented resolution of that crossing, and I'll get a two-component link, and I'm just going to let L be that two-component link. And now you'll notice that you can reobtain the knot K minus from this link L by doing the procedure of band surgery, specifically along a band B that I've drawn here inside of the ball. And then to obtain K plus, you can just add a full twist to this band. Okay, so I've just redrawn this picture here. And what the cosmetic crossing conjecture asserts is that if K plus and K minus are isotopic as oriented knots, then this two-component link L is a split link and this band B is trivial. So let me just recall that. You say that a two-component link is split if there exists an embedded two-sphere in the complement of the link that separates the two components, and the band is said to be trivial if there exists such a splitting sphere that intersects the band just once in a single component. So let me point out that triviality of the band is it's a global topological property. So even though the band looks simple, it's contained in a small ball, whether or not it's trivial depends on an entire splitting sphere for the link that intersects it in a certain way. So to illustrate that, here's an example where the link is split, but the band is non-trivial. So you can see that this two-component link is the split union of the figure-8 knot and a trefoil. But this band here is provably non-trivial. Okay, so let me tell you a little bit about what's known about the conjecture. So it's known to be true for the unknot. And what that means is if you take the unknot, you do a crossing change and obtain the unknot, then that crossing change must have been a nugatory crossing change. It's known for two-bridge knots. It's also known for composite knots conditional on the conjecture being true for prime knots. It's also known for fibered knots, for many genus 1 knots, for many Whitehead doubles. And floor homology's even been used to approach this problem, and it's known for knots whose double branch cover is an L space with an additional condition on the first homology group. And then most recently, just a month or two ago, it was shown for all genus 1 knots whose Alexander polynomial is not 1. And in particular, the conjecture is true for all prime knots with crossing number at most 9. Okay, so the conjecture has mostly been viewed as a conjecture about knots and their crossing changes. But I'd like to suggest and take a slightly different approach to this conjecture, and that's to view it as a statement about two-component links and their band surgeries. So let me illustrate what I mean. So now imagine that your starting data, instead of it being two knots that differ by a crossing change, suppose that your starting data is a two-component link and a band B. Now you can isotope the band so that the band and the link so that it looks like this local picture. And then we can let KB be the result of band surgery. So we just do band surgery along this band. And then we'll let KB plus 1 be the knot obtained by adding a full twist to the band. So I haven't really done anything. I've just replaced the notation of K plus. I've replaced it to be KB plus 1, and I've made K minus into the knot KB. And just with this very slight change of notation, the cosmetic crossing conjecture says that KB and KB plus 1 are distinct unless that two-component link we started with was split and the band we started with was trivial. So I can state what it means now for the cosmetic crossing conjecture to be true for a two-component link. So what it says for a non-split two-component link is that if you take any band B, then the knots KB and KB plus 1 are distinct. And what it says for a split two-component link is that if you take any non-trivial band B, then the knots KB and KB plus 1 are distinct. So instead of trying to prove this conjecture sort of one knot at a time until you've proven it for all knots, you could instead try to prove this one two-component link at a time until you've proven it for all two-component links. Right, so that's the approach I'd like to take today. And also, with this notational setup, I can tell you about a generalization of this conjecture called the generalized cosmetic crossing conjecture. So the initial data is the same. You have a two-component link and a band. You again let KB be the result of band surgery. But now you consider the whole family of knots KB plus N, where you add N full twists to the band. So I've drawn here two more members of this family of knots. And the generalized cosmetic crossing conjecture asserts that all of the knots KB plus N, as you vary N, they are all pairwise distinct unless the link you started with was split and the band was trivial. Right, so not just KB and KB plus 1 are distinct, but KB and KB plus N for N non-zero are distinct. And then similarly, you can say what it means for the generalized cosmetic crossing conjecture to be true for a two-component link. Okay, so let me state my main topological result right up front. And that's that the generalized cosmetic crossing conjecture is true for split links. And stated explicitly, it says that if you take a split two-component link, you take any non-trivial band B, then the knots KB plus N are all distinct. And this is the result I'd like to talk to you about today. So for the rest of the talk, L will denote a fixed split two-component link, and KB will in general denote a knot obtained by band surgery on that link. And a knot obtained by band surgery on a split two-component link is called a band sum of the two components of that split link. Now I'm also going to introduce a special notation. When the band is trivial, if you take the band sum, then you'll obtain the connected sum. So I'm going to let K sharp denote that connected sum. So K sharp is just KB in the case that the band is trivial. Okay. And throughout this talk, I'm going to be using a number of different knot invariants. And so I thought I would pose two questions about band sums for a given knot invariant that I think would be helpful to keep in mind throughout this talk. So if you've got a favorite knot invariant H, here are two questions I pose about band sums. So the first is, how are H of KB and H of KB plus N related? So I've got a fixed band B and I'm adding full twists to the band and I'm asking how does H change or how does H behave? And my second question is, how are H of KB and H of K sharp related? So here I'm comparing an arbitrary band to the trivial band. Now, the first question is sort of clearly related to the problem at hand. I want to distinguish the knots kb plus n as n varies. So I want a not invariant, which distinguishes them. But the second question is not so apparently related, but it will arise naturally. And in this talk, I'll give some sort of answers to both of these questions for knot floor homology, Khovanov homology, and instanton knot homology. Okay, so are there any questions? Okay, so let's get into it. So one nice thing about this problem that I like is that you can use the Skane relation and you can use its generalizations. So to illustrate that, let me tell you about the Alexander polynomial in this context. So the Alexander polynomial satisfies this Skane relation here. And the way we'll use it is we'll have the link J naught be our two-component link L, and then we'll let KB be J minus and KB plus 1 be J plus. And we just plug it into the Skane relation. And we find that the knots KB plus N, they actually have the same Alexander polynomial. And the proof is just that when a two-component link is split, its Alexander polynomial is 0. And you just plug it into the Skane relation. So the Alexander polynomial doesn't distinguish any of these knots at all. Unfortunate, but maybe a stronger invariant can do a little better. So knot floor homology, it's a knot invariant defined by Oshvat and Szabo and independently by Rasmussen, and it categorifies the Alexander polynomial. So the version I'll consider is h of k hat. It's a vector space over the field with two elements with two z gradings. And if you fix one of the z gradings and take the alternating sum of the dimensions in the other z grading, you obtain the coefficients of the Alexander polynomial. And it also is a functorial invariant. And I'll get to that later. All right. So what I can show is that the knots KB plus N, in fact, have the same knot floor homology. If you add full twists to this band, the knot floor homology doesn't change. So this categorifies the easy observation about the Alexander polynomial. And I'll mention that the same is true for a stronger version of knot floor homology called h of k minus. And Hedden and Watson proved this result in the special case that the split link in the background is the unlink. So for band sums of two unknots. Okay. Now there's another categorification of the Alexander polynomial, instanton knot floor homology, defined by Kronheimer and Mrofka. And it's also a vector space over the complex numbers, and it comes with two gradings, and it similarly categorifies the Alexander polynomial, and it also does not change when you add full twists to the band. Okay, so eventually I'm going to show that these knots are all distinct when the band is not trivial. So you can view these results as giving you many, many infinite families of knots, which all have the same knot floor homology. And I'm going to explain a proof of the result for knot floor homology in the context of Haggard floor homology, and the proof for instanton knot floor homology is structurally the exact same. Okay, so there are two main ingredients. The first, naturally enough, is the Skane exact triangle, categorifying the Skane relation. And the relevant triangle in our situation takes the following form. So these arrows are linear maps, and it's exact at each term. And I'll note that the horizontal map, this top map, which goes from the invariant of KB plus 1 to that of KB, it preserves both of the gradings. And so one argument you might try, which it turns out not to work, but it's a nice argument you might try. It's that we know that at the decategorified level, the invariant of L is 0. The Alexander polynomial of the split link is 0. So maybe, what if at the categorified level, this invariant were still 0? Well, by exactness of the triangle, that means that the top arrow is an isomorphism. And then because the top arrow preserves both gradings, you find that KB and KB plus 1 have isomorphic knot-Floor homologies. It's a nice argument, but it doesn't work because the knot-Floor homology of any link is non-zero. So you need a little bit more. You're not handed an isomorphism from the triangle. And the other main ingredient are maps on knot-Floor homology induced by ribbon concordances. So let me tell you about that. So let me recall a concordance between knots is an annulus properly embedded in the interval times the 3-sphere, which interpolates between the two knots. And a concordance is said to be ribbon if, when you project to the interval, you get a Morse function on the annulus with no index 2 critical points. So in general, you'll have index 0, index 1, and index 2 critical points, respectively called births, saddles, and deaths. And the restriction is that there must be no deaths in order for the concordance to be ribbon concordance. And what's relevant in our situation is that there's a ribbon concordance which goes from the connected sum to the band sum, to an arbitrary band sum. And it's a nice construction of Miyazaki's that I will tell you on the next slide. And the way we'll leverage this ribbon concordance is through the following result of Ian Zemke's. So first of all, knot-Floor homology is functorial. So a concordance will induce a grading preserving map. And Ian Zemke shows that if the concordance is ribbon, then this map is injective. And in fact, it's not just injective, it's an inclusion onto a direct summand, and you obtain a direct summand splitting. So if you've got a ribbon concordance from J0 to J1, you can write the knot-Floor homology of J1 as a direct sum of the knot-Floor homology of J0 plus something, some bigraded vector space that you a priori don't know anything about. Right. Okay, but let me give you Miyazaki's ribbon concordance construction, as it will show up a number of times. Okay, so if I want to give you a ribbon concordance from K sharp to KB, what I ought to do is I ought to start with K sharp, do a bunch of births, then do a bunch of saddle moves, and end up with KB. But equivalently, I can specify this concordance in reverse. So I can start with KB, do a bunch of saddle moves, then do a bunch of deaths, and end up with K sharp. And that's how I'll specify it. So here's my depiction of KB, arbitrary band sum of two arbitrary knots. Let me do a saddle move, and then some isotopies. Okay, let me go back and explain what just happened. So if you look right here in this diagram, the band lies in front of the knot. I do a small saddle move, and I notice that an unknot appears, and I just move that unknot out of the way and clean it up a little. And now the band lies behind the knot. So I was able to pull the band through the knot using a saddle move at the cost of picking up an unknot that goes once around the band. So now I can just freely pass the band through the knot as many times as I'd like, just using saddle moves and isotopies, remembering to always pick up an unknot each time I do it. So in this example, I do it 3 more times, and I do it until the band is trivial. And then once the band is trivial, I can then just slide these unknots off of the end and then cap them off each with a death. And I end up with kit sharp. Okay, so that's Miyazaki's ribbon concordance construction. Okay, so now I can tell you how it is that knot floor homology doesn't change when you add full twists to the band. So first I pick ribbon concordances, one from the connected sum to KB, another from the connected sum to KB plus 1, given to me by Miyazaki's construction. Then I use Zemke's result to write the knot floor homology of KB as the direct sum of the knot floor homology of K sharp plus something, some bigraded vector space that I'll just call FB. And I'll do the same for KB plus 1. And now you'll notice that if I want to show that KB and KB plus 1 have the same knot floor homologies, then it suffices now to show that FB and FB plus 1 are bigraded isomorphic, because we've found portions of each of their knot floor homologies that are the same. Okay, and that's where the Skene exact triangles come into play. So first, look at this middle triangle. This is the Skene exact triangle for the trivial band. KB is K sharp, and KB plus 1 is also K sharp. And then what you do is you pick a ribbon concordance from each of the 3 terms in this triangle to the corresponding terms in the triangle for the arbitrary band. And you pick them compatibly so that their induced maps on knot floor homology commute or intertwine with the maps in the Skene exact triangles. And what you find is not only a direct sum splitting of vector spaces, but a direct sum splitting of Skene exact triangles. So the Skene exact triangle of the arbitrary band splits as the direct sum of the triangle for the trivial band plus this triangle over here on the right. And now the triangle on the right, its bottom term is 0, because we had the floor homology of the link injecting into itself, so it has trivial cokernel. And then we have FB plus 1 mapping into FB. And then now, because this term is 0, this top map is an isomorphism, and that top map is bigrading preserving. So FB and FB plus 1 are the same. Great. So that's why knot floor homology doesn't change when you add a full twist to the band. And all of these ingredients exist in the instanton setting. So the exact same argument works. Are there any questions?
I guess I have a question. So at least in the instanton setting, on the split link, you can also put a non-trivial bundle, and I would think that would make the group vanish. Yeah,
right. If you let the arc that defines the W2 of the bundle, if it goes between the 2 components, then if it's split, that 2 sphere is there and the term will be 0. Yeah. So there's a version of this where you can make that initial argument that I said fails for knot floor homology, you can make it work in the instanton setting. Yeah. Okay. All right, so knot floor homology doesn't distinguish any of these knots, KB plus n, as you vary n. So let's turn now to the Jones polynomial and Khovanov homology. So Jones polynomial satisfies a different Skene relation, and here it is. And you can calculate what happens with the Jones polynomial as you add full twists to the band. So here's what happens. First, you just let PB be the polynomial which tautologically satisfies this equation. Then, if you add twists to the band, the way that the Jones polynomial changes is that it's still a sum, one term being the Jones polynomial to connected sum, but the other term is our PB, this polynomial, multiplied by some high power of Q. And you obtain this from the Skene relation plus the fact that the Jones polynomial of a split link is, it's not 0, it's a factor times the Jones polynomial of the connected sum. And so that's how the connected sum shows up in these formulas. Right, but you'll notice that we're in a much better position now to show that the knots KB plus N are all distinct. We can potentially distinguish them with the Jones polynomial. So if PB happens to not be the 0 polynomial, if it's just not the 0 polynomial, then when you multiply it by a power of q, it becomes a different polynomial. So as long as PB is not 0, the knots KB plus N all have distinct Jones polynomials. So our question is, well, is PB non-zero whenever the band is non-trivial? But you'll notice that asking whether or not PB is 0 is the same thing as asking whether or not KB and K sharp have the same Jones polynomial. So really the question that we're asking now is, does the Jones polynomial detect the trivial band? Is PB non-zero whenever the band is non-trivial? Now, I don't know the answer to this question, and in general, it's pretty hard to answer questions of this form. Does the Jones polynomial detect some topological property of interest? But it's turned out that it's more reasonable and sometimes possible to answer a categorified version of such a question. So before trying to answer this question about a categorification, let me first categorify this observation about how the Jones polynomial changes when you add twists to the band. Okay, so Khovanov homology, introduced by Khovanov, categorifies the Jones polynomial, and I'll take it to be a vector space over the field with 2 elements. And it comes with 2 gradings, denoted H and Q. And if you fix the Q grading and take the alternating sum of dimensions in H grading, you obtain the coefficients of the Jones polynomial. And it's also a functorial invariant. And in fact, it satisfies actually the same behavior under ribbon concordances. So if you take a ribbon concordance, Levine and Zemke show that you get a injective map on Khovanov homology, and in fact, you get a direct sum splitting. So we can take our ribbon concordance, given to us by Miyazaki's construction, and get a splitting of the Khovanov homology of KB as the direct sum of the Khovanov homology of K sharp with something. And bigraded vector space, finite dimensional, and I'll just call it HB. And now you'll notice that if you decategorify this isomorphism, you take graded Euler characteristics, you see that it says that the Jones polynomial of KB is equal to the sum of the Jones polynomial of K sharp plus the graded Euler characteristic of HB. But PB tautologically satisfies an equation of that form, so it follows that the graded Euler characteristic of HB is PB. So you can think of HB as a categorification of PB, if you'd like. Right, and this is how the Jones polynomial behaves when you add twists, just copied from the previous slide. And here is how Khovanov homology changes when you add full twists to the band. So what happens is that the Khovanov homology of the connected sum, it just sits there stationary. It doesn't move, it's always a direct summand. But this extra bit, it undergoes a grading shift. So it's just this old HB, but shifted in its H grading and in its Q grading. And you'll notice that the Q grading shift is exactly the power of Q you see at the decategorified level. But the H grading shift is invisible at the decategorified level because it's shifting by an even number. And throughout this talk, I've been talking about adding full twists to the band, but you could instead consider adding just half twists. And if you add half twists, Khovanov homology changes in the way you would want. The Khovanov homology of the connected sum always just remains sitting there, but the moving part, it just moves half as far. Okay, so here's how to see this. The proof is actually very similar to the argument I gave for non-Floor homology. So in Khovanov homology, there are also skein exact triangles, but they're different. They're the unoriented skein exact triangles. And the relevant ones I've drawn here, there's two relevant ones. And we play the same game. So we consider the triangles for the trivial band, and we pick compatible ribbon concordances from each of those terms into the triangles for the arbitrary band. And Levine and Zemke's result gives us a direct sum splitting of these triangles for the arbitrary band as the direct sum of the triangles for the trivial band, plus these triangles over here on the right. The bottom terms of the triangles are 0 again, so the top arrows are isomorphisms. But the key difference between the Khovanov homology argument and the not-Floor homology argument in this context is that these arrows in the skein exact triangles of Khovanov homology are not grading preserving. They actively shift the gradings. They shift the gradings by 1, 2. So HB and HB plus 1 they have the same dimension, but they're not bigraded isomorphic. They're bigraded isomorphic after a grading shift. So that's how this result goes. Okay. So now we're in a pretty good position to distinguish the knots KB plus N. We know that the way that the Khovanov homology groups are changing is that you've got a stationary part, and then you've got HB, and it's moving as you add these twists. So if you want to distinguish all the knots, you just have to show that that moving part is not 0. It's not the 0 vector space. So the question is HB non-zero whenever the band is non-trivial? Does Khovanov homology detect the trivial band? And that is what I prove. So the dimension of Khovanov homology of KB is equal to the dimension of the Khovanov homology of K sharp if and only if the band is trivial. And this is where the main work goes into for the result. And as a corollary, the generalized cosmetic crossing conjecture is true for split links. The knots are all distinguished by their Khovanov homology groups. And I'll note that Hedden and Watson, they first showed that the Khovanov homology groups of the knots KB plus N are all distinct when the split link is the unlink. Okay, and I'd also like to point out a small subtlety here. So if you take a non-trivial band, you form KB. A priori, it could be isotopic to K sharp, because triviality of the band is defined in terms of the existence of the splitting sphere. It's not defined in terms of what knot you get. Miyazaki shows that, in fact, if KB is isotopic to K sharp, then the band had to have been trivial. And it also follows from this result up here, because this condition is that the band is trivial. The condition is not that KB and K sharp are isotopic. Okay, so I'd like to tell you about how I prove that Khovanov homology detects the trivial band. And the proof goes, as many other proofs, that Khovanov homology detects some topological property of interest. What I do is I relate it to a floor homology. I prove the result I want for the floor homology. Then I show that my connection between the Khovanov homology group and the floor homology group is strong enough that I can lift this to a Khovanov homology detection result. So let me first tell you about how I reduce to a floor homology. So here's what I need to make this reduction argument. All I need is a not invariant H, which is a vector space. And I want it to have a spectral sequence from Khovanov homology. But the key thing that I need is that it's functorial. So what I mean is that I want that if you have a concordance between knots, I want an induced map of spectral sequences, which on the Khovanov homology page induces the Khovanov homology map. So for example, you could take H to be the Hegel-Floer homology of the double branch cover of the knot, and you could also take it to be singular instanton homology of the knot. Okay, and I claim that if you have such an invariant, then if the dimension of H detects the trivial band, then the dimension of Khovanov homology also detects the trivial band. So suppose you've got a band for which KB and K sharp have the same dimension Khovanov homology. Goal is to show that the band is trivial. You pick a ribbon concordance from K sharp to KB, and you look at the induced map of spectral sequences. Now on the Khovanov homology page, on the E2 page, say, you know it's injective because it's the Khovanov homology map. It's the result of Levine and Zemke. But then you also know it's surjective because of the dimension assumption. So it's an isomorphism on the E2 page. And then it's just a fact about maps of spectral sequences that if you've got an isomorphism on a given page, it's an isomorphism on the rest of the pages and on the E infinity page. So it's an isomorphism on the E infinity page. And so the dimension of H of KB is equal to the dimension of H of K sharp. And then because the dimension of H detects the trivial band, you conclude that the band is trivial. Okay, so to prove that Khovanov homology detects the trivial band, you have a number of options. You can prove it for any Floer homology that has a functorial spectral sequence from Khovanov homology. And so we're back to Floer homology, and the route that I take is through singular instanton homology. And I show that singular instanton homology detects the trivial band. And really the proof is that instanton not Floer homology defined using sutured manifolds, that version detects the trivial band. The singular instanton homology version is the one that has a functorial spectral sequence from Khovanov homology. Okay. But another route that you might imagine trying to take would be through not Floer homology. So Dowlin he constructed a spectral sequence from Khovanov homology to not Floer homology. And I can show that not Floer homology also detects the trivial band. But unfortunately, Dowlin's spectral sequence is not known to be functorial. So I don't know how to take this not Floer homology detection result and use it to show that Khovanov homology detects the trivial band. Right. So I actually figured out how to prove this result for not Floer homology a good while before I figured out how to do it for singular instanton homology. So I found myself in the situation that I could either try to prove functoriality of Dowlin's spectral sequence, or I could try to adapt my not Floer argument to the instanton setting. And they both seemed challenging for me. But eventually I got it to work for instanton homology. Okay, so I'm going to tell you my argument for not Floer homology, and then I'll tell you the adaptations needed, or some of the adaptations needed to make it work in the instanton setting. Okay, so are there any questions before I get into it? Okay. So the goal is to show that when the band B is non-trivial, that the dimension of H of K hat of KB is strictly larger than the dimension of H of K hat of K sharp. That's the goal. So here's KB, along with a gray unknot that goes once around the band that I've labeled C. And I want you to consider this two-component link, KB union C. Now this link has a very nice topological feature, and it's that C bounds a disk disjoint from KB if and only if the band is trivial. That's equivalent also to saying that this two-component link is split if and only if the band is trivial. So Right, so this two-component link sees triviality of the band in a very nice way. And in fact, you can easily show that the link floor homology of this two-component link detects the trivial band. You just use Thurston norm detection. But that's not what we want. I don't want to show that the link floor homology of this link detects the trivial band. I want to show that the not floor homology of KB detects the trivial band. But I want to use the nice topological features of this link, the fact that it can see triviality of the band in a nice way. So really what I want is a version of link floor homology that contains the information of the dimension of the not floor homology of KB. So that's the sort of thing I want. And let me tell you what the version, which version of link floor homology I want to use. So first of all, a Hager diagram for this two-component link will have 4 base points, 2 corresponding to the knot KB and 2 corresponding to C. And I want to define a minus version of link floor homology. And it won't be the standard version, but specifically what I want is, so I have a chain complex freely generated over the ring F adjoin U, generated by the Hager generators, and the differential counts disks that are blocked by 3 of the 4 base points. So it's going to be blocked by both base points corresponding to KB and one of the base points corresponding to C. And the disks are allowed to pass over the remaining base point by just record algebraic intersection numbering the power of U. So this isn't the standard version of link floor homology, but it's a standard construction in Hager floor theory. And I claim that if you take the homology of this version of link floor homology, and I've added this sigma here to remind you that it's a funny version of link floor homology. I claim that this version of link floor homology, it contains the data of the dimension of not floor homology of KB. So in particular, if you take this F adjoin U module, you look at its rank is twice the dimension of the not floor homology of KB. Okay, so let me elaborate on that. So now abstractly as an F adjoin U module, this link floor homology group is isomorphic to the direct sum of a number of copies of F adjoin U plus a number of copies of F adjoin U mod U to some power. Now these latter summands are called U torsion towers, and the copies of F adjoin U are called infinite U towers. And the rank is just the number of infinite U towers. Now you obtain that the link floor homology group is isomorphic to such a direct sum from the fact that this chain complex actually has a Z grading. So this chain complex has the Alexander grading corresponding to C, it's a Z grading, and U drops it by 1. So whenever you've got an F adjoin U module and it has a Z grading that U drops by 1, you get a structure theorem of this sort. Okay, and then this equality, this claim, it comes from an exact triangle. It comes from the exact triangle shown here. The top 2 groups are just this link floor homology group, and this bottom group is the not floor homology of KB tensored with a 2-dimensional vector space. Now in the Hager floor context, this exact triangle comes from, in a fairly straightforward way, from just writing down a short exact sequence of chain complexes. The injective map of that short exact sequence is U minus the identity. And you just take the long exact sequence and you get this triangle. But in the instanton setting, this triangle is a little harder to access. Right, but once you have this triangle, you obtain this claim just by using the structure theorem. So you observe that a U torsion tower, U minus the identity, is an isomorphism on a U torsion tower. Whereas on an infinite U tower, U minus the identity is injective, but has dimension 1 cokernel. So each infinite U tower corresponds to a dimension of this vector space down here.
So shouldn't it be the other way, the claim? Shouldn't the 2 be on the other side then?
The 2 comes from the fact that this.
Oh. Okay.
This vector space here is twice the dimension of H of A hat.
Right.
Okay, so right, so the point of this was that I've now converted a problem about knot floor homology into a problem about link floor homology, and I can now use this two-component link. Okay, so the new goal is to show that the rank of this link floor homology group of KB union C is strictly larger than the rank of this link floor homology group when of K sharp union C when the band is non-trivial. So I want to show there are more infinite U towers over here than there are over here. Okay. So right off the bat, what we can do is we can take Miyazaki's ribbon concordance construction and get a ribbon concordance from K sharp union C to KB union C, and then use Zemke's argument to obtain a inclusion of the link floor homology group of K sharp union C onto a direct summand of the link floor homology group of KB union C. And it's an inclusion onto an F adjoint U module direct summand in a grading preserving way. So in particular, every infinite U tower in the invariant for K sharp union C gets mapped onto an infinite U tower of the invariant for KB union C. So to show that there are more infinite U towers, to show that the rank is larger, that's equivalent to showing that there's an infinite U tower over here that does not lie in the image of this map. Just want to find an additional infinite U tower. Okay, and to do so, one observation you could make is that if you look inside the invariant for K sharp union C, you look at all the infinite U towers, you can just calculate that, in fact, all of the generators of these infinite U towers, they lie in the same Alexander grading. This is the Alexander grading corresponding to C. So the whole U tower won't lie in a particular grading because U drops grading by 1, but you can look at the top grading in which the U tower exists, and if you just take a homogeneous generator of that U tower, look at the Alexander grading, they will all lie in the exact same Alexander grading. And so the images of these infinite U towers, they will also all start in the same Alexander grading. So if you want to find an infinite U tower that does not lie in the image, it suffices to just find 2 infinite U towers whose generators start in different gradings. If you find 2 such towers, then at least one of them is not in the image of this map. Okay, and now that's a statement that's entirely internal to just the link floor homology group of KB union C. I had my initial goal was a comparison between 2 knot floor groups. It became a comparison between 2 link floor groups. And now the problem is internal to a single link floor group. Okay, and then to find these 2 infinite U towers, I use sutured manifolds and sutured floor homology. So let me just remind you that if you start with a sutured manifold, for example, the sutured exterior of KB union C, and if you do a surface decomposition, a nice surface decomposition, you'll get a balanced sutured manifold. And Juhas defines a floor homology group for the sutured manifold, and he proves that it sits as a direct summand of the sutured floor homology group of the original sutured manifold. In our case, it would just be the link floor homology of this link. Now, I'm not using normal link floor homology in this context. I'm using a minus version, a funny minus version of link floor homology. So what I need to use is not just sutured floor homology, but a minus version of sutured floor homology. And I can't just decompose along any old surface. I place some restrictions on the possible surfaces that I'm allowed to decompose along. So in particular, if I take a decomposing surface, which is disjoint from the torus boundary corresponding to C. I'll get a new sutured manifold with the torus boundary corresponding to C, still a torus boundary component. And you can define a minus version of sutured floor homology of this sort of sutured manifold. And it's a relatively Z-graded F adjoint U module. And it sits as a direct summand of the original sutured floor homology, of the original link floor homology. So it sits inside of there as a relatively Z-graded F adjoint U module summand. So the point is that if you could now find two infinite U towers inside of this sutured floor homology group, whose generators lie in different gradings, then you've found two towers inside of the link floor group, whose generators lie in different gradings. Right, so then the game becomes, can you cut along surfaces, always staying away from the torus boundary corresponding to C, until you arrive at a sutured manifold whose sutured floor homology you can compute explicitly and find those two infinite U towers that lie in different gradings. And that's what I do. So I adapt some of Gabai's work on band sums, his superadditivity of genus under band connected sum. And I show that if you start off with the sutured exterior of KB union C, and if the band is non-trivial, then there exists a sequence of surface decompositions, always disjoint from the torus boundary corresponding to C, that takes you all the way down to the sutured exterior of a hop link. And then the hop link, I can compute its floor homology, and I see that from direct computation that its link floor homology group has two infinite U towers whose generators lie in different gradings. So that's the argument. Are there any questions?
I think we should thank Josh for a lovely talk.
Oh, sorry, I actually.
Oh, that wasn't your.
I apologize. That wasn't yet.
Okay,
Let me
well,
pause. Let me pause.
well, I'll be quiet and let people ask questions and let you continue.
Okay, so, but thank you though. So let me comment on some of the techniques that you need to develop to adapt this argument to the instanton setting. So first of all, you need minus versions of instanton homology. And luckily for me, this had been developed recently by Baldwin Civic, Lee, Ghosh Lee, and others since then, initially based on ideas of Ednar, Belovic, and Zarev in the context of behavior floor theory. And what's important in this argument is this module structure, this C adjoint U module structure, along with gradings. And so I proved some technical results about gradings in this instanton context. And one of the key things that I needed is that the rank of this module of the invariant for KB union C is twice the dimension of the usual instanton non-floor homology of KB. And in making this argument work, something that came out of this was that if you take a null homologous knot in a closed oriented three manifold, then the dimension of its instanton non-floor homology is at least the dimension of the instanton homology of the three manifold itself. And this was later generalized to rationally null homologous knots. Right, so I developed some of this theory, minus versions of instanton homology. And then what I needed for my argument is a behavior of a minus version of sutured instanton homology under suitable surface decompositions, and a behavior of this minus version of instanton homology for links. I need a behavior of it under ribbon concordance. Okay, so let me review. So at the beginning of the talk, I posed two questions about band sums for any given knot invariant. And here are some of the answers from the talk. So the first question is, how are h of kb and h of kb plus n related? If you add full twists, how does the invariant change? So not-floor homology doesn't change. Instanton not-floor homology doesn't change. But Khovanov homology changes as long as the band is non-trivial. The second question is, how are h of kb and h of k sharp related? And I show that all three of these homology theories, they all detect the trivial band. And I'll end on a comment about the non-split link case of the generalized cosmetic crossing conjecture. So I've proven it for split links. So what remains are non-split links if you're taking it from this approach. And you can just see from the skein relation that if the generalized cosmetic crossing conjecture is false for a given two-component link, then its polynomial invariants look like it's a split link. So what I mean is that its Alexander polynomial will vanish, its Jones polynomial will be divisible by Q inverse plus Q, and the Humphrey PT polynomial will be divisible by this factor. So one approach you might take would be to show that a categorified invariant of L looks like that of a split link, and then try to prove that that categorified invariant actually detects that the link is indeed split. So a result you might try to use is that the module structure on Khovanov homology, it detects whether or not the link is split. And this is a result of Lipschitz and Sarkar. And I proved the analogous result for link floor homology, that there's a module structure on it and it detects if the link is split. So unfortunately, though, I don't know how to go from the assumption that the cosmetic crossing conjecture is false for the link L to a statement about the module structure on the link floor homology of L. But this is a future research direction. So thanks everyone for listening.
We can thank him a second time now. Are there further questions?
Just in sort of a speculative vein. So I guess, there's the famous, question of approach to the question of whether the Jones polynomial detects the unknot by saying, well, that you can express that you can calculate the volume for hyperbolic knots in terms of some crazy computation that you do with the Jones polynomial, which I can never remember. So do you think there's some kind of similar, I don't know, volume-ish approach to this, to a sort of a different sort of proof of the result you have?
I'm not so certain about a volume conjecture approach to the result that I have, but I did think a little bit about trying to use some kind of volume conjecture type statement to prove it for the non-split link case. And so I think that that community does have a version of the volume conjecture for links, and it's somehow a little special for split links, but for non-split links, I've seen a statement where it predicts something. And I think that it's probably possible to, I mean, I don't know for certain, but I think it's interesting to ask, like, does that conjecture actually imply the cosmetic crossing conjecture? And I think that maybe that might be true. Yeah, it's somehow some sort of statement that the colored Jones polynomials of a two-component link should somehow say that the link should somehow see if the link is split or not.
I have a question.
Sure.
Sorry, I wasn't sure if you were done or not. So sorry, this is like kind of a roundabout question, but like when you're showing that not floor homology, right, like doesn't detect whether you like adding full twist to these bands, right? And like, another route that you could probably prove it is like by using like tangle decompositions, right? And of course,
Yeah.
I like your proof better because it's more like conceptually sound. But I was wondering if you could turn your result like backwards and show like that this implies like some sort of like generalized mutation invariance in like Zebrauius's tangle theory, like that if you like, decompose
so
and then like twist, right, like doesn't change like the action of the mapping
Right.
class group. Yeah.
So I don't think you can go from a result like I have to a statement about that tangle invariant, because the statement is something like you take this invariant, you pair it with something else, and then it doesn't change. That's not going to tell you that the thing itself doesn't change. But Claudius and Artem and Liam and some other people have been thinking about this conjecture from that point of view of the tangle invariant. Specifically, one of the tangles is just part of the band, and the other tangle is the rest of it. And they can actually recover, and they can actually prove a lot of these results as well. So yeah, so they're also thinking about the case where the link is not split, and in their picture, it's not so relevant whether or not the link is split. It's just whether or not the band is trivial. But yeah, so they can show that when the link is, or they can show that in general, as long as the band is not trivial, that the dimensions of Khovanov homology on either side, as you add more and more twists, they diverge. So the knots eventually also start to become different. And they have other results too that recover some of the things that I've proven.